Hello and welcome back to EGR 171 Fluid Systems. In this unit, we're going to be looking at the standards and symbols used in the fluid power industry.
While the standards we see today seem relatively complete and cover most of the information you'll need to know about fluid power systems, these have actually evolved over time. Essentially, what they've been designed to do is make sure that systems work together well, and when companies work together, the fluid power systems function appropriately, and essentially we're all on the same page. What they try to do is make sure that things like size, shape, weight are all standardized, and as a result, when you compare them, if for example you're talking about a 1 horsepower pump, essentially you know that the output of a rated 1 horsepower pump will be pretty close to the same, regardless of what organization you purchase it from. Now, these standards have been developing, as I said, over time, and a number of different organizations have been involved. We have, of course, manufacturers within the fluid power industry. We have a number of different standards organizations that are specifically involved in the creating and maintaining of them. We also have things like state government, federal government that set up these type of standards and other type of regulations, as well as the insurance industry. They are heavily involved in maintaining the safety regulations, oftentimes in industry, so they may appear as well. Now, in the fluid power industry, there are a number of different groups, including the National Fluid Power Association, NFPA, Fluid Power Distributor Association, FPDA, International Fluid Power Association, IFPCS, and the Fluid Power Education Foundation, FPEF. Keep in mind, these are in addition to sort of broader standards groups, including ANSI, previously known as the American National Standards Institute, and ISO, the International Standards Organization. So these are broader organizations that oftentimes incorporate some of these fluid power and other areas into their standards. Now, when we talk about fluid power symbols, the idea is to represent them clearly and in a standard way across the industry, and I should say a clear and efficient way. So what these symbols may include is things like design features, how the thing is actually put together, and how our system or circuit is going to function. There are a number of different types. The simplest is the graphic symbols. Those are referred to as the ISO graphic symbols. That's one we're gonna spend the most time on. But keep in mind we also see pictorial symbols, cutaway symbols, and combination symbols. We'll talk briefly about those as well. As I said, the graphic symbols are our most common type. They are essentially a series of lines and arcs used to represent the different components and our conductors, etc. They're going to be organized in squares, triangles, circles, etc. And each of those represents a different functional item. Keep in mind they're very simple. They don't necessarily show what the object looks like or a lot of details about sizing, because they're designed to be simple enough so that you can quickly sketch them if you want to do a hand sketch. And in addition, of course, these are going to often be available in your CAD software and as predefined blocks or symbols that you can use. Generally, what they represent is the internal operation. So for example, we see a two-position valve on the side here. The operation is indicated by the arrows. This is where the flow is going to go. This spring over here indicates it's a spring return. This indicates the solenoid. Don't worry, I'm going over this quickly. We'll go into more detail on all this later on. But what this represents is how the valve actually is supposed to function. As I said, this is standardized. So around the world, we use the same symbols for hydraulic and pneumatic systems. And this allows for easy, efficient, and hopefully clear communication. Now, pictorial symbols, on the other hand, represent what the what the component actually looks like. So if you look here on the right, we have a single acting cylinder. You actually can see it. You can see a line going in at the bottom. You can see the where the actual rod is going to extend outward. For example, here's a three-way directional control valve. You see the three lines going into it. This is a button on the end, right? So pretty much all the details of the components are going to be shown. Now it is simplified, right? We're not showing exactly how the component is put together necessarily. We're not showing, for example, any labels or anything else on it, but it does show piping placement, right? It does show where the hoses or tubing is going to enter the actual components. That's particularly important. And in general, we'll see that the form is standardized, right? Although the shapes may change between manufacturers slightly, the actual pictorial symbol is pretty consistent from manufacturer to manufacturer. Now, cutaway symbols actually show the inside of the device. So we're back to that same two components, this single acting cylinder over here and this three-way directional control valve over here, but now they've been sliced open. And what they're designed to do is show how the system functions on the inside and hopefully assist in things like troubleshooting where you could find a way or be able to tell what potentially could go wrong. Now, these are very rarely standardized. The fact is, every manufacturer is going to be slightly different because they build their device in different ways. But this is the most accurate representation. The idea is so you can actually see inside the device. So we want to make sure it's as accurate as possible. Now, in terms of the illustrator, there really isn't a lot of guidelines associated with it. You do, of course, want to show things clearly. So how's the fluid going to flow? How does the fluid come into the device, right? If there is something that's actually going to function, how does that operate? How does it move? And keep in mind that it may not be completely accurate because devices do change over time and things can be modified during construction. So important to realize that even though you have a cutaway diagram, it is distinctly possible that something in the manufacturing or something in the actual assembly might have modified the details. Lastly, it should be noted that you can actually combine the symbols in a circuit diagram. So for example, here we see our pictorials of our cylinders, but we see ISO symbols for our valves. And we actually see cutaways down here for some of our other directional control valves and our pump. Now, generally, this is when you want to highlight specific areas. So for example, you may want to show the absolute function of your pump, and that was why you may want to use a cutaway. This isn't really a standardized approach, but if you're a situation where you need to specify certain things in more detail than others, this is something that is acceptable in terms of the industry, but you will probably rarely see that. Now, if, for example, though you're a pump manufacturer, you might see a cutaway symbol of the pump and all of the rest of the circuit done with ISO symbols. That would make sense. But in general, if you're involved in the assembly and troubleshooting of hydraulic symbols, you'll see one version or the other and not combinations, because this could lead to some confusion. So there are some general rules that apply to the use of all of these various types of symbols. Keep in mind the primary purpose of these are to communicate to the user what type of component is going to be in a circuit, what that component does, and how that component is connected to the other components that make up the circuit. Generally, you'll see basic symbols used, but keep in mind these can have additional elements, particularly when you're trying to show more complex functions. In general, you will only see the external ports shown on a symbol. So how does it connect to other components? You don't tend to see the internal functions unless, of course, you're looking at a cutaway. In terms of where those ports are, these are shown in symbolic form, so you really have to represent where they actually are located on the valve. Valves differ from manufacturer to manufacturer, but we're mostly worried about function, not so much about the actual appearance. In terms of the symbols themselves, they can be rotated to fit in a diagram better or to indicate function better. But in general, we're limited to 90-degree increments, so they're vertically, horizontally, etc. In certain situations, however, you can use other orientations. So for example, if you have a hydraulic cylinder that is mounted at, say, 30 degrees, you may want to represent that as being mounted at 30 degrees in the actual diagram, because that communicates an important feature of it. Right. So, but it is probably important to note it somewhere that that 30-degree increment is used for a specific reason. So let's get started on the various symbol types. The fact is, lines are used in our diagram to represent a number of different things. If, for example, you see a solid line, that represents a conductor, something like a hose or a tubing or something like that. And there's actually going to be flow during normal operation. Pilot lines are designed to sense pressure. Essentially, it connects a certain component to another area of the circuit, and we sense that pressure for it. It's usually used for essentially mechanical remote control. And by the way, if you don't really understand all these functions that I'm mentioning, don't worry about it. We will get into more detail when we discuss each of these components in a separate chapter. In addition, we have titer dash lines that represent drains. Essentially, these are often situations where we want to make sure that fluid will be able to drain out of a component if something happens. And lastly, we use a long dash, short dash line to represent component enclosures. Essentially, when we have multiple components in one device, we actually use this long dash, short dash line, similar to a center line in drafting, to wrap a line or a box all the way around the device. In terms of our components, we try to use the shape to represent some of the functionality. So for example, when we draw something as a circle, this is going to be a rotary device of some type. There's going to be rotation involved. So the common rotary devices we're going to see are things like pumps, compressors, and motors. In terms of squares, they're going to indicate a variety of different type of control components, things like valves, etc. And conditioning apparatus is shown actually as this diamond pattern. Right? Conditioning apparatuses are things like filters or strainers, etc. If you have a longer rectangle, that might be a valve with multiple positions or a cylinder. If we see a U-shaped half rectangle, right, where it's just the half of a rectangle, that represents a reservoir, essentially a tank. Lastly, you'll see, in rare occasions, capsules, essentially with rounded ends on them. And what there are any device that is essentially holding pressure. Right, so these can be things like a pressurized reservoir, receiver on a pneumatic system, or an accumulator in either of a pneumatic or a hydraulic system. In addition, many of the symbols are going to have these additional elements added that indicate some type of function. Right? So for example, a common one is the use of an equilateral triangle. Right? You can see it here on this motor. And this indicates the flow direction. They're used when we have large levels of flow. So you won't see these necessarily on things like drain lines or pilot lines. But anytime there is energy movement taking place, you're going to see these triangles used. If the triangle is filled or solid, like shown here, that's going to be for hydraulic components. If this triangle was empty, right, essentially hollow or open, that would be used for pneumatics to indicate the difference between, say, liquids and gases. We'll also see arrows being used. So for example, on this motor is able to rotate. It's able to rotate in both directions. So that curved line indicates that there's some rotation. The fact that it has two heads, it means it can rotate in either direction. Straight lines, on the other hand, most often represent some type of variability. In this case, for example, the straight line at a slope indicates that it's going to be adjusted, right? There's going to be an adjustment associated with it. So this is a flow control valve that's adjustable. Anytime you see that inclined arrow, it means that there's something that can be varied in the device. You also see arrows being used to indicate flow and fluid movements, but they tend to be straight lines, horizontal, vertical, etc. This slope line is particularly used for adjustability. These various elements will be attached to the device itself. So for example, here we see a 2-position valve, 1, 2. There is spring control. It's actually attached right to it. Some devices we're going to see are going to have some type of metering. We'll see this narrowing here. This indicates that there's an orifice involved where it's going to limit the amount of flow. Right? So they're going to be either attached, or if there's a separate device, we may see them enclosed in that long dash, short dash line to indicate that they're incorporated right inside the device. That you wouldn't see them as 2 separate devices because the actual functionality is internal to the component. One of the simplest but most important things we need to show is how individual conductors are connected. So for example, here, when we want to show a T-type connection, you'll show the 2 lines coming together and a dot is used. This is important because without this dot, the question would arise, are those 2 connected there together, or are they just close to those locations? You do want to avoid when lines cross like this for a dot. So for example, if you do see multiple lines coming together, the preferred approach is to separate them. And the idea is to, again, just show them as clearly as possible. If, on the other hand, when you're drawing things, you do not want to show that the fluid lines are connected, we show this with a little loop over the top, right? In general, we try to avoid crossing lines when we draw a circuit diagram, but in some cases it's impossible. So in those cases, you're going to have lines that are not joined that have to cross in the diagram. Show them with this loop added to indicate that they are not connected. You'll see straight lines. You'll also see these curved lines. Straight lines indicate a rigid conductor, something like a pipe or tubing. If you have a flexible hose, something that's going to be bendable, then oftentimes you use this slight loop in here, again connected to the 2 rigid lines to indicate that. Many devices, particularly in situations where we have connections that are going to be able to be changed, we have quick disconnects. Right? You may have used those if you ever used a hydraulic system on, say, a plow or a skid steer, or you may have used them if you've ever used, say, a nail gun or any type of air wrench. And quick disconnects are shown here. These are shown connected. If the symbol was split in half and there was a gap between the 2, that would show them as disconnected. And by the way, in your diagrams, what you want to show is how they are normally set up. What is the normal condition? In addition, we need to show how individual components are controlled or potentially provide control. This is most common on valves, but you will see them on other devices as well. So for example, one of the most common ways to control the valve is have an operator actually move something, right? So for example, they could push a button, right? Or they could activate a lever, right? So this is going to be something that the human operator actually does. In addition, we can oftentimes see some sort of mechanical operation. So for example, a spring. A spring can be used so that when the valve is actuated, when the pressure is removed, it goes back to its original position without the operator having to do anything. For example, things like self-centering or self-actuating valves would use a spring. We may also have a situation where one component activates another. So a roller device could be used. So when one part touches this, it activates the actual valve. In many situations, we have pressure in one location, right? So something happens in one location in the circuit, and that causes another component to function. This is sensed by using pressure, in most cases pilot pressure. We could connect them with liquid in the system, that would be hydraulic. If you saw, for example, a hollow dot, you could use pneumatics. And the fact is, we can have devices that use hydraulics and pneumatics in combination in the same circuit. In addition, we may see some type of feedback, something sensing that then causes an electronic control. So for example, a solenoid, which is essentially a magnet-operated device, uses some type of sensor, which then may be powered in a way to open or close this solenoid. And again, we'll talk about more in detail of all these various things when we talk about valves.